And now it's my great honor to introduce our next speaker to give the opening keynote. Dr. Santer is an atmospheric scientist, Dr. Benjamin Santer. He's an atmospheric scientist at Lawrence Livermore National Laboratory. He's a member of the National Academy of Sciences, a recipient of a MacArthur Fellowship and many other prestigious awards for his work. He studies the natural and human fingerprints in climate records, work that has proved significant in attributing human activity to climate change. And in 1995, it wasn't so clear that there wasn't such a broad consensus on climate and climate change. And Dr. Santer was the lead author of the detection and attribution chapter of the Intergovernmental Panel on Climate Change second assessment report. And he penned the scientific finding that was groundbreaking for the time. The quote is, "The balance of evidence suggests a discernible human influence on global climate." And this was the first major authoritative scientific review identifying humans as a driver in climate change. And it came with personal cost. But to quote Dr. Santer, if you spend your entire career trying to advance understanding, you can't walk away from that understanding when someone criticizes it or criticizes you. So please join me in welcoming Dr. Santer, who will give his personal reflections on progress since the threshold breaking 1995 IPCC finding.
Thank you very much, Lauren. Good morning, ladies and gentlemen. I'm going to talk to you today about what happened 25 years ago and about the genesis of the balance of evidence finding that Lauren mentioned. So two life-changing events happened to me. One was when I was 21, falling in a crevasse in the French Alps and climbing out and being alive. That changed my perspective on things. The other life-changing event happened in November 1995 in the Palacio de Congresos in Madrid. It was here from November 27th to 29th that the Intergovernmental Panel on Climate Change, IPCC, Working Group 1, met in order to finalize the summary for policymakers for the second assessment report of the IPCC. But before telling you about what happened in this building in Madrid, I want to back up 5 years to the first assessment report of the Intergovernmental Panel on Climate Change. Back in 1990, the Climate Change Detection and Attribution chapter of the first assessment report essentially said the jury is still out. This was their bottom line finding. The unequivocal detection of the enhanced greenhouse effect from observations is not likely for a decade or more. Well, in 1995 in Madrid, as Lauren mentioned, this was the bottom line conclusion, these famous 12 words. The balance of evidence suggests a discernible human influence on global climate. And it was really the first time that the international scientific community spoke with one voice and said, we've looked at the scientific evidence, most of it is pointing in the direction of a clear human influence on global climate. So it turned out that one of the key pieces of evidence that led to that transition between the jury is out to yes, humans are affecting climate was climate fingerprinting. And the basic premise in fingerprinting is that different influences on climate have different characteristic signatures or patterns. And those signatures are easier to discern if scientists look past one number, for example, the global mean temperature of the surface of the Earth, and look at things like altitudinal patterns of climate change, which is what you see here. These are computer model simulations, slices through the atmosphere from the North Pole to the South Pole, from the surface nearly to 30 kilometers. And in climate model world, you can run simulations where you only change one thing at a time, the sun's energy output, according to our best understanding of how that actually changed. Human-caused greenhouse gas increases, particulate pollution, volcanic aerosols after massive volcanic eruptions, human-caused ozone depletion. And you can understand the fingerprints or patterns that each one of these factors produces in the climate system. That's powerful. And it turned out that in 1995, the scientific community was already conducting these pattern-based fingerprint studies, and their evidence contributed to this balance of evidence finding. And I'm now going to give you a quick sense of the power of fingerprinting. So as I mentioned, this is our best shot, our best estimate of global scale changes in the average temperature of Earth's land and ocean surface. This is from a NOAA group, the National Oceanic and Atmospheric Administration. Other groups produce pretty similar results. Our best understanding is that the average temperature of the Earth, land and ocean, has increased by about 1.1 degrees Celsius, nearly 2 degrees Fahrenheit, since 1880. And one common assertion about such temperature change is that it's all due to the sun. There's been an increase in the sun's energy output, and this warming is a purely natural process. So how might fingerprinting help us to address this kind of incorrect all surface warming is due to the sun claim? Obviously, this is not drawn to scale. This is a Simpsons kind of view of the sun and the Earth. But imagine if that kind of criticism were correct, and all of that surface warming of roughly 2 degrees Fahrenheit were due to an increase in the sun's energy output since 1880. What you would expect to see then would be essentially more sunlight arriving at the top of the atmosphere, again, not drawn to scale here, and heating throughout the full vertical extent of the atmosphere. So an obvious question, if you're a scientist, is how has atmospheric temperature actually changed in its vertical structure? Well, we can answer that question. Also, from NOAA polar orbiting satellites, we have these beautiful measurements of the microwave emissions of oxygen molecules. And we've measured these microwave emissions since late 1978, and they are proportional to the temperature of different broad layers of Earth's atmosphere. So by measuring at different microwave frequencies, you can literally back out the temperature of the lower atmosphere, the mid to upper troposphere, as it's called, and the lower stratosphere. And you can look at this pattern of atmospheric temperature change, in this case from the South Pole to the North Pole, and from the surface right up to 20 kilometers. And this is actually from a group in California. Some of the preeminent remote sensing scientists in the world actually work in Santa Rosa. And their estimates, in common with estimates from other groups, show this curious dipole pattern of warming of the lower atmosphere, the troposphere, and cooling of the upper atmosphere, the stratosphere. This is over the full 41-year satellite record from 1979 through to the present. And just a few features. First of all, the largest warming of the lower atmosphere is over the Arctic, where we've seen about a 40% decrease in the extent of Arctic sea ice, again, over the satellite period. And the decrease in temperature in the stratosphere is large over the Antarctic ozone hole, but it's also been non-negligible over the tropics. The key point here is that this pattern, this fingerprint of warming low down and cooling up high, is fundamentally inconsistent with the claim that an increase in the sun's energy output causes all surface warming. Such claims face two fundamental difficulties. One is the cooling of the upper atmosphere, and the other is that we've actually monitored the sun's energy output from space, and over the time we've measured the sun's energy output, something called total solar radiance. There's been an increase in surface and lower atmosphere temperature, but no measured increase in the sun's energy output. So this gives you some sense of the power of looking at patterns and the power of fingerprinting. It can help us to discriminate between different proposed hypotheses about the causes of climate change. Now back to Madrid and back to this now 25-year-old history. What happened in this building with this beautiful Miró mural on the face of the building? Well, my first reflection, I'll give 4 personal reflections during this talk, is that what happened in Madrid really did change the world. These 12 words, the balance of evidence suggests a discernible human influence on global climate, forced the scientific and international scientific community to recognize that humans were now active agents of change in the climate system. We were no longer just innocent bystanders. And during these 3 days in Madrid, I came to understand the power of language. In the plenary sessions, particularly on November the 29th, 1995, the governments and scientists involved in the report spent many hours deliberating the language. And much of the attention focused on the strength of the evidence. Was balance of evidence the correct capturing of our then available scientific understanding? Or should it be stronger? Should it be weight of evidence, preponderance of evidence? There was recognition in Madrid that the language would be translated from English into French, German, Russian, Chinese. And the nuances of language really mattered. Things like weight versus preponderance of evidence had different legal implications. What was the correct verb to capture the information from over 140 different scientific studies? Was it suggests, or was that too weak? Should the verb be indicates, demonstrates? These were all discussion points in Madrid. And perhaps the major discussion point was the qualifier on the size of the human influence. Should that qualifier be significant, identifiable, detectable, measurable, appreciable? I came away from Madrid with a profound sense of the power of language. When someone tells you words can't change the world, that's not true. My personal experience was they can, and they did. What were the key criticisms of that discernible human influence finding? I would split them into 2 categories. There was what you might call non-scientific criticism, or just plain nonsense, that the balance of evidence finding represented some corruption of the peer review process, that there was political tampering, and perhaps the most odious criticism was scientific cleansing. This was at a time that ethnic cleansing was going on in Bosnia, and the criticism said that all scientific uncertainty had been purged from the detection and attribution chapter, which was completely untrue. As Secretary Blumenfeld mentioned, this was sort of an alternate view of reality, an alternative view of what had actually happened. But then there was also valid scientific criticism of that balance of evidence finding. And I would categorize it as 2 different thrusts of criticism. One was there's too much focus on temperature in detection and attribution work. If there really is a human-caused climate change signal lurking in observations, it should be manifest in many different aspects of the climate system, not just in temperature. Go look for it in many different indicators of climate change. The other valid criticism was that back then, in the early 90s, climate scientists had not done a particularly good job in quantifying the size of the human effect on climate and in making informed statements about the relative sizes of human and natural climate change. So let's look at some of these things, some of the scientific criticisms. My second reflection is, do the research required to address the criticism? I'm proud of the fact that our group at Livermore and the international scientific community took these valid scientific criticisms to heart and did the research necessary to address them. This isn't just a pretty picture you see here. This is the amount of water vapor in the atmosphere. We measure water vapor from space using something called the Special Sensing Microwave Imager. It looks directly at microwave emissions from the hydrogen line. And in this beauty here, you can also capture the global scale changes of atmospheric moisture and determine whether the atmosphere is or is not moistening. This gets directly at the criticism, don't just look at temperature. So in 2007, our group found that there was indeed some human-caused signal in the moisture content of Earth's atmosphere as monitored from space. The atmosphere was moistening, and that this signal was primarily due to human-caused increases in well-mixed greenhouse gases. This study was criticized too, and the criticism was, it's not a model democracy. We had done this fingerprint study looking at water vapor with 22 different climate models whose identities have been skillfully disguised here. And the criticism was, you folks have given each of these 22 models one model, one vote, but it's not a democracy. Some models are better than others. And what you see here is water vapor and its variability on two timescales, 2-year timescales and month-to-month timescales. And the crosshairs are focused on the satellite water vapor measurements. And the colored dots are the model results in these 22 different climate models. You can see that there's a very large range, roughly a factor of 5, in the ability of climate models available back then in the mid-2000s to capture the observations. So the criticism was, why don't you have a do-over of your fingerprint study with the top 10 climate models? Figure out which are closest to this observational target, the satellite data, and repeat the analysis with those top 10 models. So we did that. Again, responding to valid scientific criticism by doing the research required to address the criticism. So what you see here are 12 different ways of selecting the top 10 climate models out of that bunch of 22 climate models. And these are model simulations with human-caused increases in greenhouse gases and human-caused changes in particulate pollution. The kicker here is that if you look at these 12 different collections of top 10 and bottom 10 climate models, the patterns, the fingerprints of water vapor change in response to human influence are all remarkably similar. Water vapor increases everywhere, and the largest increases in water vapor are over the warmest areas of the tropical oceans. Why? That's basic physics. If you ramp up CO2 and start warming the ocean and the lower atmosphere, you increase the moisture holding content of the atmosphere by about 7% per degree C increase in temperature at the surface of the ocean. And that's exactly what we saw in all of these models, irrespective of how we selected them. If you look at the same top 10 and bottom 10 models, but now at their patterns of natural climate variability, you see very different patterns. These horseshoe type structures here with water vapor increases and decreases are El Nino variability shining through. These are so-called control simulations that have no human-caused increases in greenhouse gases. So warming the planet leads to a fingerprint that you can see here that is very different from patterns of natural climate variability. And the satellite observations of water vapor change look much more like the fingerprint, the human influence fingerprint, than the noise of natural climate variability. So again, we responded to criticism here, two forms of criticism. You're only looking at temperature. No, we looked at water vapor. It's not a model democracy. Look at the better models. We did that. It didn't make a difference because the physics that drove water vapor changes was well represented in models irrespective of their quality. So for this particular example, which models we used didn't make a difference. Just to wrap it up here, I've given you one example with water vapor, but climate scientists have identified human fingerprints not only in temperature and in water vapor, but in atmospheric circulation patterns and sea level pressure, in the expansion of the tropics and movement of jet streams, in not only water vapor, but in rainfall, in runoff from major river basins and surface-specific humidity, in Arctic sea ice extent, in Northern Hemisphere snow cover. And in each of these cases, literally dozens of different aspects of climate change, scientists have looked at complex patterns of change and have found that the changes in these different variables are physically and internally consistent. And these are changes that are independently monitored by a wide range of different platforms in the ocean, at the Earth's surface, and from space. So the bottom line from all of this work is that it's this internal and physical consistency of many dozens of lines of evidence that gives us confidence in the reality of human effects on global climate. So from the cautious, even wimpy, as some would say, the balance of evidence suggests statement in 1995, in its third assessment report in 2001, the IPCC concluded that most of the warming observed over the last 50 years is attributable to human activities. So they addressed that 1995 criticism. You have not done, scientists, a good job at quantifying the size of the human effects. They tried to do that in 2001, in 2007, in the fourth IPCC assessment, and in the most recent assessment report in 2013, the fifth assessment. And look at this calibrated likelihood language. Scientists said, we think we can now say with considerable confidence, so extremely likely meant greater than 95% probability that the statement was correct, that human influence has been the dominant cause of observed warming since the mid-20th century. How was this progress made from the jury is out in 1990 to extremely likely in 2013? I would argue that progress was made because we have better climate models that are more complete in their representation of the Earth's system. We've transitioned from models of just the atmosphere and the ocean surface to full atmosphere-ocean models with integrated carbon cycles, with atmospheric chemistry in them, with much more complete representation of physical processes that are important in the climate system. Back in the 1990s, we had a small number, half a dozen, of major modeling centers that were developing atmosphere-ocean models. Now we have many dozens of models, enabling us to do statistics across models and look at uncertainties and projections of future climate change, look at uncertainties, as I've showed you, in the fingerprinting work that arise from differences in model quality. Back in the 1990s, we largely focused on human-caused changes in greenhouse gases. There has over time been better scientific understanding of the complexity of human influence on the climate system. We don't just burn fossil fuels and change greenhouse gas levels in the atmosphere. We've transformed the land surface by deforestation. We produce particulate pollution. And scientists increasingly have tried to understand and represent those forcing factors. We have longer observations than we had back in the 1990s, and in particular, a much better understanding of critical components of the climate system that are areas of uncertainty in climate modeling, of the ocean and of clouds. We now have standard model simulations that we ask all climate models to perform in order to better understand how well they do in their atmospheric components, in their ocean components, and in many other components. We've crowdsourced the analysis of model simulations. Back in the 1990s, an individual modeling group focused on its own simulations and was often reluctant to share that simulation output with the entire atmospheric sciences and climate community. Now that sharing is part of the price of participating in large national and international climate assessments. We have, through things like the Earth System Grid Federation, efficient software tools for sharing petabytes of simulation output and satellite data in order to facilitate the scientific interrogation of model simulations. We have better statistical methods for evaluating models and for doing climate fingerprinting. And more importantly, I think, most importantly, we have a greater diversity of scientific expertise trained in climate science. Climate science is not just the purview of atmospheric scientists, computer scientists, biologists, economists, social scientists, and that increasing entrainment of experts with many, many different areas of expertise has been to the benefit of the overall improvement in our understanding of the complex climate system and human influence on it. So what's next? The next IPCC assessment will be coming out sometime next year. What will they conclude? What will their focus be? In my opinion, one focal point will be the focal point of these 2 days here, looking at connections. And this is from work done by Robert Rohde at UC Berkeley. This shows you essentially California's fire season. And on the x-axis, temperature during May to October, and on the y-axis, precipitation during May to October over California. And you can see that over time here, we've transitioned to hotter, drier weather. And during that transition to hotter, drier weather in California, we've experienced the largest and most destructive wildfires. So I think that fingerprint detection work will increasingly focus on impact-relevant variables and on looking at things like wildfires that are directly relevant to human lives and livelihoods. I just wanted to show you one final example from our own work. Again, this relates directly to connections, and it relates to the two things I've talked to you about today, water vapor and temperature. So it turns out that in the tropics, there's a very tight relationship in all climate models between the moistening of the atmosphere and the increase in temperature. And you see that here. These are older climate models, newer climate models. These are so-called large ensembles performed with individual climate models. And irrespective of which models you use, older, newer, you see that there's this very tight relationship between water vapor change and temperature change in the tropical atmosphere. Now I'm going to add the satellite water vapor and temperature measurements to this figure, and you can see they're all over the map. There's about a factor of 2 difference in the basic observations in this relationship between water vapor change and temperature change, with one particular satellite data set here showing something that is far, far removed from any of the model results at all. What this tells us is that there is likely some problem with the observations. The measured moistening of the tropical atmosphere is too large for the measured warming of the tropical atmosphere. And it seems to be that there's still some underlying error in the satellite temperature data that we need to understand. So this illustrates the power of looking at these connections between different independently monitored variables. And this isn't just some abstruse example here. Temperature data has been the focus of congressional investigations. And what I've learned, reflection 3, is that as a scientist, you have a responsibility not only to do the best research you can, but also to enter the public arena when the science that you do comes under unjustified political attack, and to defend that hard-won scientific understanding. I think there's little point in being a scientist if you're unwilling to use your voice and speak out on what you've learned and why it matters to others. And there are often these extraordinary opportunities of using your voice. This was my 5 minutes of fame on Late Night with Seth Meyers, where I had an opportunity to rebut incorrect claims made by Senator Cruz about the very satellite temperature data I've talked about today. So if you have a voice, use it. Finally, and this relates to comments made by Chairman Lopez at the beginning and by Jared Blumenfeld as well, that these are not just science issues. I've talked to you about evidence, but this is not just about science. This is also about our human values. And what I'm going to show you now are pictures that I've taken over my lifetime as a climber in the Alps, in the Himalayas, most recently the Juneau ice field in Alaska. And over one human lifetime, I've witnessed profound places in these beautiful, fragile, high alpine environments. What value do we place on these environments? What value do we place on clean air, clean water? Do we place on intact tropical rainforests? We have to have some discussion about these values, not just about the science and about the fingerprinting, but about the kind of world in which we want to live and the kind of world we want our kids and grandkids to live in. This last picture here is taken at a place called Heather Camp, looking down onto the immensity of the Gilkey Glacier. It's a beautiful place. If you ever have the opportunity, go and see it. Since 2001, the surface elevation of the Gilkey Glacier has decreased by about 150 feet. Change is rapid, not only on the Juneau ice field, but also many, many other beautiful places in our world. So let's have a discussion not only about the science, but also about the value of these places and the kind of world in which we want our kids and grandkids to live. Thank you for the extraordinary opportunity to speak to you today. And I'm delighted to be a part of this two-day conference.
Thank you so much for a very fascinating and motivating talk. We do have some questions coming in, but we don't have time for a Q&A. So we're going to encourage everyone to use the Slack. And Dr. Santer, if you wouldn't mind checking out the Q&A and responding to those comments, that would be fabulous. So thank you so much.
I'd be happy to do that, Lauren.